sorry about that. There was a minor technical difficulty, and so I'm going to continue the rest of this lesson in this second video. So where I left off was just that want to find the area of this triangle, and so the area of this triangle is half the area of this parallelogram. So this is equal to half the area of that parallelogram, which we said is the norm of this vector and that vector. I'm going to call the vectors u here and v here. So actually I'm going to call this u, I'm going to call that v, okay? So P1, P2 I'm going to call u, and P1, P3 I'm going to call v, so we don't have to write all that down. So it's going to be half the norm of the cross product of those two vectors. Half the area of the parallelogram determined by those two vectors. And so what we have to do is calculate the norm of those two vectors. And so we know that the norm of u cross v is equal to the norm of u times norm of v times sine of the angle between them. Sorry. That would be good, but we don't have the amplifier, so we're going to do it slightly longer. We're going to find u cross v and then take the norm. Okay, so u cross v is equal to the determinant of this matrix, where u, so here u is p1, p2, right? And what that vector is it's this vector p2, negative 1, 0, 2, minus p1, which is 2, 2, 0. Okay, so this is the point p2 minus p1. So the vector p1, p2, it starts at p1, ends at p2, is the point p2 minus the point p1. That's p2 minus p1, and what you get for u is negative 3, comma negative 2, comma 2. Okay, so u is negative 3, negative 2, 2. Okay, so that's u. And then if you find v, v is just p1, p3 there. So P1, P3 is the point P3 minus the point P1. And what that's equal to is the point P3 minus the point P1. Okay, and that's equal to negative 2, comma 2, comma 3. So V is that vector. And so I'm going to put the components of V here. Okay? Right, the first component of V, the second component of V, the third component of V. That was the first component of U, second and third component of U. Okay. So that's u and v, and now I want us to take their cross product, and so what we get is, computing this cross product, you would get the norm of negative 2, 2, 2, 3, comma negative the norm of negative 3, 2, negative 2, 3, comma the norm of negative 3, negative 2, negative 2, 2. And so practicing finding the determinant of the matrix, you get that. And this is equal to this times this minus that times that, which is negative 6 minus 4, that's negative 10, comma negative 9 plus 4, which is negative 5. And then negative 6 minus 4 is negative 10. And so you get negative 10 this is negative 9 plus 4, which is it's taking the negative of negative 5. That's a positive 5 there. It won't make a difference in the final answer, but it's still, technically, it has to be positive 5. Okay, so negative 10, comma 5, comma negative 10. That's u cross v. Okay, so in your notes, before I erase something, norm u cross v is that. Okay, you can pause it if you want to look at these calculations and to check the determinants of these matrices and the operations in it. See how I did it. Okay. So that's u cross v. So u cross v, just so I have more room, I'm going to rewrite this. U cross v was negative 10, comma 5, comma negative 10. And then the norm of u cross v is the norm of that vector, right? And how do you calculate the norm of a vector? You take the square root of the sum of the squares of its components. And so the sum of the squares of its components are negative 10 squared plus 5 squared plus negative 10 squared. And so you add up the squares of its components and you take the square root of the sum. So this is equal to the square root of 100 plus 25 plus 100. Right? Negative 10 squared is 100, 5 squared is 25, negative 10 squared is 100. So this is the square root of 225, and that's 15. Okay? So now the norm of u cross v is equal to 15. Okay, and I'm just going to plug that in here. The area of the triangle is equal to 1/2 the norm of u cross v. That was the fact. Okay, that's the fact there. And then that's equal to 1/2 times that norm, which we found was 15 here. So the area of the triangle is half of 15. That's 15 over 2. That's the final answer. Find the area of the triangle. Find the area of the triangle. We found it there. We were done with the problem. Okay. Okay, so definition 2. So if u, v, w are vectors in 3 space, then u dot v cross w is called the scalar triple product of those 3 vectors. Of u, v, and w. So if u, v, and w are 3 tuples whose components are real numbers or vectors in 3 space, then u dot v cross w is the scalar triple product of u, v, and w. Okay, and what is the scale? What is that? What is u dot v cross w? What is that, and why would that help? U dot v cross w is equal to the determinant where the first row are the components of u, the second row are the components of v, and the third row are the components of w. And so actually this determinant, that's what u dot v cross w is, right? These are the 3 components of u, first, second, third components of u, first, second, and third components of v, first, second, third components of w in R3. Okay? So this u dot v cross w, which is that determinant, is called the scalar triple product of vectors u, v, and w. This is equation 7 in this section. Okay, so equation 7 is really important. It's good to know. And so as a note here, right, when I told you that u cross v was equal to the determinant of I, j, k, u1, u2, u3, d1, v2, v3, right? So we proved that in the board that u cross v, the way I defined u cross v was equal to that determinant. Well, that determinant is the scalar triple product of the sorry. Okay. This. No, it's fine. Okay, no, everything I do is, let's forget about it. Forget that note. Everything else is good. Okay, So then, that is equation 7. Okay. Okay, so example 5. If u is the vector 3, -2, -5, v is equal to so if u is that vector, v is that vector, and w is that vector, then u dot v cross w is equal to, so it's going to be equal to, I'm just going to take the components of u, which are 3, -2, -5, components of v, 1, 4, -4, 0, 3, 2, and so you're just going to find u dot v cross w, determinant of that matrix, and you find the determinant of that matrix, and it's 3 times the determinant of that matrix minus -2 times the determinant of that matrix plus -5 times the determinant of that matrix. Okay, so applying the cofactor expansion along the first row of this matrix, you get that. I mean, if you did the first column or the third row, it might be easier because there's a 0 there. Right? So I didn't do it the fastest way, but I just go with the first row sometimes. So 3 times the determinant of this, which is 8 minus -12, which is 20. Minus -2 is plus 2. So 2 minus 0 is 2, plus -5 times 3 minus 0, which is 3. Okay, and so this is equal to 60 plus 4 minus 15. It says 64 minus 15, which is 49. Okay, so u dot v cross w is 49. And so in this example, we found the scalar triple product of the vectors u, v, and w given. It's 49. That's a 9. Okay. Okay, so now we have the definition of a scalar triple product and an example of calculating it. Okay, and another note, from equation 7 on the last board, we get that u dot v cross w is equal to w dot u cross v, which is equal to v dotted with w cross u. So I'll remind you what 7 was. 7 was u dot v cross w is equal to that determinant. It was how to calculate the scalar triple product. Okay. Right. So it's not necessarily so obvious why this would give you that. So I'll quickly explain. Okay. So this was 7 from earlier. That's the same equation from before. I'm not saying a new equation. So from earlier, last board, u dot v cross w is equal to that determinant. So this u dot v cross w, this determinant, is equal to that, right? So u dot v cross w is the determinant of that matrix. Now, if I wanted to know the value of this expression, w dot u cross v, it will be the determinant of the matrix where the first row, or the w, is the components of w, the second row is the components of u, and the third row are the components of v, right? W, then u, then v. Here, u, then v, then w. So the question is, what is this, right? This is that. Well, I want to show that this determinant is equal to that determinant. That would show that these two are equal. Okay? Well, what elementary row operations could I perform on this matrix to get that one? Well, what I could do is I could switch. I want the third row to be the first one, so I could switch the first and third rows. And the W would be here, and the U would be in the third row. Then after I switch the first and third row, I could take the new third row and switch it with the same second row and get that. And so the elementary row operations was, first I could switch the first and third rows, right? If I did that first, then I switched the second and third. After I did that, switch the second and third rows. Right? So I start with this matrix, I switch the first and third rows, then after I do that, I switch the second and third rows. And by earlier lessons, we learned that if you know the determinant of a matrix, if you switch two rows of a matrix, the determinant of the resulting matrix is equal to, the relationship between the new and old matrix are the determinants are negative of each other. And so by switching two rows of a matrix, the change in the determinant is you get the negative of the original determinant. And so the determinant of this matrix, if you switch the first and third rows, the determinant of the new matrix is the negative of the old one. But then if you switch two rows again, you're then taking the negative again of that matrix, of the determinant of that matrix. And so by switching two rows twice, the determinant of the new matrix is just multiplying this by -1 twice. And so the determinant of the resulting matrix is equal to the determinant of the original matrix. You just switch two rows twice. Each time you switch two rows, the determinant of the resulting matrix was the negative of the old one. And so then doing that twice, you now get that this determinant is equal to that determinant. And because this is this and this is that, the determinants that these two things are equal to are the same, and so they're equal. Okay? And so similarly, you can show that this is equal to that by switching rows of the matrix whose determinant is equal to those things. Okay? And you'll just get, just very similarly, you can show this is equal to that. And then all three of them are equal. Okay? Okay. So theorem 3.5.4a, the absolute value of, so the absolute value of the determinant of u1, u2, v1, v2 is equal to the area of the parallelogram in two space. In R2, I'm going to say R2 instead of two space. Save room. In R2, determined by vectors U, which is U1, U2, and V, which is V1, V2. Okay, so theorem 3.5.4, the absolute value of that determinant is equal to the area of the parallelogram in R2 determined by vectors U and V. Okay, so to illustrate this, if you have the vector U here and you have the vector V there, right? And then, but these are vectors in two space. So here's the x-axis and y-axis, and these vectors are both in R2. Then those two vectors living in R2, they determine a parallelogram, and then if you take the absolute value of the determinant of that matrix, that's the area of the parallelogram determined by those two vectors in two space. Okay. That's the shaded region. The area of that shaded region, that's the area of the parallelogram determined by U and V in R2. Okay, and B, the absolute value of the determinant is the determinant of this vector u1, u2, u3. So the absolute value of the determinant of that is equal to the volume of the parallel is equal to the volume of the parallel pipette. So it's equal to the volume of the parallel pipette in 3 space, determined by U, which is U1, U2, U3, V, which is V1, V2, V3, W, which is W1, W2, W3. There are 3 vectors, U, V, W, in 3 space with those components. Okay, we're always using the same notation for the components of the vectors. Okay, so the absolute value of the determinant of that is equal to, so the absolute value of that is equal to the volume of the parallel pipette in R3 determined by U, V, and W. It's basically just the 3-dimensional shape with vectors U, V, and W as sides of it. So for instance, you have the same initial point for U, V, and W. So here's U, V, and W. It's the box. It's kind of like a box where if U, V, and W all start at the same point, it's a box determined by U, V, and W. And that box doesn't necessarily have to be a normal box. It can be slanted, but it's pretty much box. Right? You wouldn't want to get a delivery with one of these boxes, but the idea is it's the shape of the box that's might be a little slanted or directed in a weird direction. Okay, good. Okay, see that box? And so that has sides U, V, and W as part of the box, where they all start at the same initial point. So the area of that 3-dimensional thing, the area of that entire 3-dimensional region inside the box, that area is equal to the absolute value of the determinant of that matrix. Okay? Okay, so you can pause the video here if you want in order to write this down and draw the pictures and so forth. These vectors are in R3. So this space, this is living in R3 here. This is already living in R2 there. And so I don't want to draw the X, Y, and Z axis here, like I did X, Y there. I don't want it to interfere with the box I drew. But this is all in, there's the X axis, there's the Y axis, there's the Z axis. You can say the origin is there if you want. Okay. Okay, and in the book, you can look at figure 3.5.7, and that illustrates this example. Okay, so figure 3.5.7 in the book illustrates this example, and I drew my own pictures for this here. But you could look at very similar pictures in that figure to this. Okay. Okay, so remark, V, which is the volume of a parallel pipette, determined by U, V, W. So capital V, which is the volume of a parallel pipette determined by U, V, and W, that's equal to the absolute value of U dot V cross W. Okay. So the parallel pipette I drew before, the volume of that right? Because we're in 3 space. So quantifying the amount of space something takes up in 3 space is a measure of volume. And so we're finding a volume in that last board. Because the volume of that parallel pipe determined by U, V, and W is equal to the absolute value of U dot V cross W. The scalar triple product of U, V, and W, right? This is the scalar triple product of U, V, and W. Absolute value. Okay. Right, and the absolute value of that is equal to this vector. I mean, this determinant from earlier. So this is equal to that. So theorem 3.5.5. If U is this vector, V is this vector, and W is this vector, these are just 3 vectors in 3 space, 3 vectors with 3 components, real number components. If U, V, and W have the same initial point, then they lie in the same plane. Look at the then here. Then they lie in the same plane. That statement that they lie in the same plane is equivalent. Remember, this is the biconditional symbol. This means if and only if, which is abbreviated by IFF. And what that means is they have the same truth value. So the words, you could replace the biconditional symbol, this notation you could replace with the words has the same truth value as. So the statement they lie in the same plane has the same truth value as U dot V cross W is equal to, which is this, by definition of a scalar triple product between 3 vectors. The statement is that the scalar triple product of U, V, and W is equal to 0. So I'm going to circle this, and so this is a visual way of seeing the statement. And oftentimes it's easier to digest something if you can figure something out, if it's more visual. Okay. So theorem 3.5.5, if U is that vector, V is that vector, and W is that vector, there's 3 vectors in R3. If they have the same initial point, then the statement that they lie in the same plane has the same truth value as the statement that their scalar triple product equals 0. Okay? So the conclusion of this statement, the conclusion of this theorem, is not telling you that something's true or false. The conclusion of this theorem is saying that this statement has the same truth value as that statement. And actually, just like a lot of other theorems, it is actually very useful to know that 2 statements have the same truth value. Even without the conclusion being something is true or false, knowing that 2 things have the same truth value is actually a very powerful statement to make. Because if I can determine the truth value of either of these statements, I know the truth value of the other statement. Okay, so this theorem, theorem 3.5.5, you can use it to when in conjunction with knowing whether one of these is true or false, you can use this theorem and know the other statement is the same truth value. Okay, and so an illustration of this theorem would be, for instance, if you have the vectors U and V, right? And they're on the same plane. Okay, so on the same plane doesn't mean they have to both be on the XY plane, right? If you're in 3 space, you could have 2 vectors both up in the air, kind of, and they could be in the same plane. You just need to have some plane that goes through those 2 vectors, okay? So it doesn't have to be a particular plane that they coexist on. You just need to be able to find a plane where they do. Okay. Oh, sorry. And there's 3 vectors. So there's 3 vectors. So let me put this here. So U, V, W are on the same plane, right? So illustrating it. So if U, V, and W are on the 3 vectors are on the same plane, not a particular plane, you can find some plane where all 3 of them are on, where they all have the same initial point. So you have to put all of them on the same point. The initial points of all your vectors have to be at the same point. That would imply the fact that you can put them all three of them on the same plane. That would imply that their scalar triple product is 0 by theorem 3.5.5. Okay, so without doing any calculation, if you can take vectors u, v, and w at the same initial point with the same initial point, and you can put them on some plane, then you can deduce from that by this theorem that their scalar triple product is 0. Okay, without a calculation. And how this theorem also helps is if you calculate the scalar triple product of u, v, and w, and you get that the scalar triple product of u, v, and w is 0, that implies by this theorem, because they have the same truth value, those two statements, that then they lie on some same plane. That they lie on the same plane. Make sense? Okay, so you don't have to just go in one direction here. You can show one of them is true. And then if you show one of them is false, if the scalar triple product was non-zero, if it did not equal 0, then you would know that it would be impossible, that you couldn't put the three vectors on one plane. Because since saying it's equal to 0 would be false, it would also be false to say that they lie on the same plane. Okay, so there's a lot of ways this actually could be used. Okay, and so that's the end of 3.5. Okay, so we are done with 3.5 in this example. Okay, so we actually I wanted to talk a little bit about chapter 4, but instead of talking about chapter 4, let's stop at the end of 3.5 and let's instead talk just for a few minutes about the first exam. Okay, so again, exam 1 is on April 13th this year, 2020. It's a Monday. Okay, so exam 1 for this class, Math 231. Okay, you might be watching videos from another class, right? I have them both on the same YouTube page. This is for Math 231 linear algebra. Okay, right? So for linear algebra Math 231, exam 1 is on April 13th, 2020. And it's a Monday. Okay, the test starts at 8:30 p.m. Okay, so by starts at, I mean everyone show up. I'm going to start getting things ready, and then when we're ready, we'll start. Okay, so at 8:30 p.m., I posted the instructions on Blackboard on Monday. Okay, so yesterday I posted the instructions on Blackboard, and so I'm just going to say a little bit of it again. It's a lot though, so you have to read what I posted. But we're going to start the exam at 8:30 p.m. on Monday, April 13th. It's very important that you download Zoom. Okay? Download Zoom. It's an app. So on whatever device, whatever computer you're going to take the exam on, Zoom has to be on that computer, right? If you're using your computer to take the exam, downloading Zoom on your iPad will not help, right? Zoom has to be on the device that you're taking the test on. So you have to download Zoom, okay? So do that. Also, you have to learn how to use Zoom. So practice using it. Okay, so consider this really important homework, more important than a normal day's homework. It's very important that you practice using the app Zoom after you download it, okay? Practice it by turning it on, call someone on it, figure out, see that you can have a conversation with someone. Practicing it is not just so you can know how to use it. You have to make sure that your video works and your sound works, okay? You have to make sure that you can hear someone, that you can see someone, that they can hear you, that they can see you. You have to make sure your internet will stay on, that your internet doesn't turn off. You have to make sure your internet is reliable, okay? If any of these things are a problem, maybe you have a friend or a relative that you can visit for a short amount of time who they don't mind if you use their internet that's more reliable, or maybe use their computer that works better or well, or maybe you don't have a computer, you need to use someone else's for the test. Okay, but in any case, at 8:30 p.m. on Monday, I'm going at exactly 8:30 p.m. on Monday, April 13th. I'm going to post a link on Blackboard. Take that link, copy it, paste it onto your web browser, go to the site, and it'll bring you to the Zoom meeting. So you'll have Zoom ready downloaded. That link will bring you to Zoom. Say you want to join the meeting, you'll be in the meeting, and then there'll be about a 10-minute period where I wait for everyone to get on, and I start proctoring exam and telling you the rules, and then we'll start the exam. Zoom has a 40-minute max time length for meetings that take up more than 2 people. And so I want to use Zoom because I'm comfortable with it, and there's problems with everything, but I'm comfortable with Zoom, and it hasn't really given me a problem. So I want to use Zoom. So what we're going to do is that we're going to half hour the test in one meeting. We're going to end the meeting at the end of the half hour. Immediately when I end the meeting, there's going to be another link on Blackboard, which will say second meeting, second part of the test. Do the same thing, copy that link, paste it onto your web browser, join the second meeting immediately after the first one ends, and then there'll be another 30 minutes for the rest of the exam. Okay? You'll have to email me your answers after the test, and you'll have to do it. You'll need an email address, you'll need a reliable internet connection to send it, you'll need some way of making copies of your answers. You can take pictures with your cell phone, you can scan copies if you have a scanner. If you can do neither of those things, maybe there's another way you can do it. If you can't think of a way to do it, do you have a friend or relative you can go to their house and they can make copies for you? I mean, they have a scanner that you can use to make copies. If there's no way you can do all of this, you need to contact me via email. My email is michaelpendazis spring2020@gmail.com. It's on the syllabus. I mention it a lot. It's on Blackboard. You need to email me and let me know that there's a problem if there is one. So Monday I posted all the rules and instructions. All the instructions are Blackboard. Read everything. It can explain to you exactly what to do next Monday. Okay, so I'll see you then. Bye.